Welcome to our latest video on the topic of aldehydes and ketones, nucleophilic addition. This video is suitable for A-level students. By the end of this video lesson, you should understand that aldehydes and ketones react with hydrogen cyanide to form hydroxynitriles and that these reactions are examples of nucleophilic addition. You should also be able to write chemical equations and reaction mechanisms to describe these reactions, and be aware that hydroxynitriles undergo hydrolysis reactions to form important hydroxyacids. In our previous videos on aldehydes and ketones, we've learnt that aldehydes and ketones are a series of compounds that contain the C double bond O group or carbonyl group. And in aldehydes, the carbon atom of this group is joined to at least one hydrogen. So the general formula of an aldehyde is RC double bond O H, and R is shorthand for an alkyl group. Examples of aldehydes are shown here. We have ethanol, which has 2 carbons and is an aldehyde. We have propanol, which has 3 carbons, and we have butanol that has 4 carbons, and all have an alkyl group attached to a C double bond O and a H. Now in ketones, the carbonyl is joined to 2 other carbon atoms. So the simplest ketone must contain 3 carbons, and the general formula of a ketone is RC double bond O R, and once again R is shorthand for an alkyl group, e.g. a methyl group. And 2 examples of a ketone are shown here. We have propanone, which has a CH3 attached to a C double bond O and then another CH3, and butanone, which has a CH3 attached to a C double bond O and then CH2, CH3. And notice that the alkyl groups can be the same as in propanone, they're both CH3 groups, or they can be different as in butanone. We have a CH3 attached to the C double bond O and then a C2H5 group. Aldehydes and ketones undergo nucleophilic addition reactions. And in a nucleophilic addition reaction, a pair of electrons from a nucleophile attacks the delta plus carbon in an aldehyde or ketone, and it forms a coordinate bond to this carbon. The general mechanism is shown here, and you can see a pair of electrons attacks the delta plus carbon, and this is shown by a double-headed arrow. Now the carbon is delta plus because it's next to an oxygen which is more electronegative. So that's why the carbon is delta plus and the oxygen is delta minus. Now when the nucleophile's pair of electrons attack the delta plus carbon, this causes the double bond between the carbon and the oxygen to break. And I represent this by drawing a double-headed arrow from the middle of that bond to the oxygen. Now this is the slow step in this reaction, and it's a 2-step process. Now this step has caused an intermediate to form, and the intermediate has a single bond between the carbon and the oxygen, and this oxygen has a negative charge. Now around this oxygen I've put 3 lone pairs of electrons. This is because there was 2 lone pairs on the oxygen when there was a C double bond O. And when I broke that bond, the pair of electrons in the bond is now also on that oxygen. So there's 3 lone pairs of electrons around the oxygen. And a pair of these electrons can attack a H plus ion. Now, a pair of these electrons attack the H plus, and I represent this by a double-headed arrow. Now this causes a coordinate bond to form between the H plus and the oxygen on the intermediate. And when this forms, I have my final product. And in this final product, you can see that the nucleophile has bonded via coordinate bond to the carbon, and a hydrogen in the form of H plus has also formed a coordinate bond to the oxygen to make an OH. Now when the carbonyl group of an aldehyde or ketone is attacked by a nucleophile, an addition reaction occurs and the carbon-oxygen double bond is broken. Now this first step, the nucleophile's pair of electrons attacking the delta plus carbon and the carbon double bond oxygen breaking, is a slow step. And the intermediate then gains a proton to form the final product. Now this gaining of a proton, this pair of electrons attacking the H plus to form the OH, is a much faster step. Now aldehydes and ketones undergo a nucleophilic addition with hydrogen cyanide, and the nucleophile in this reaction is a cyanide ion, a carbon triple bonded to a nitrogen with a minus charge, a negative charge on the carbon. And the reaction is carried out by adding dilute sulfuric acid to an aqueous solution of the aldehyde and ketone dissolved in potassium cyanide. Now, the reason that the sulfuric acid is added to potassium cyanide is this is how hydrogen cyanide is made. It's made as part of the reaction. It's made in situ. And you can either use potassium cyanide or sodium cyanide, but when you add dilute sulfuric acid to either, you make hydrogen cyanide gas. Now, hydrogen cyanide gas is a toxic gas that attacks the central nervous system, so great care has to be taken here to prevent the hydrogen cyanide escaping into the air. Now, if we look at the equation here, we have an aldehyde, ethanal, but we could draw a ketone because it works with either, plus hydrogen cyanide, and we get a compound called a hydroxynitrile. Now, when naming the compound, the nitrile group takes precedent, so that's why it's a nitrile and not an alcohol. And you have to find the longest chain that contains the CN group, the nitrile. So if we look at the compound that's formed here with ethanal, the longest chain has 3 carbons in, and there's a OH group attached to the middle carbon. Now carbon 1 is the CN group, so therefore the OH group is on carbon 2. So this compound is called 2-hydroxy propane nitrile. And notice that we've added a carbon to the chain. Ethanal had 2 carbons in it. This compound has 3 carbons. So this is a great way of adding a carbon to the chain. Now the reaction is classed as a nucleophilic addition because it involves attack by the nucleophile, an electron pair donator, in this case the Cn-, and the overall addition of hydrogen cyanide across the CO double bond. Now it's also worth mentioning that in the product that forms 2-hydroxy propane nitrile, there's a carbon attached to 4 different groups. We have a CH3 attached to the carbon, a CN attached to the carbon, an OH attached to the carbon, and a hydrogen. Now this is a chiral center, so therefore 2-hydroxy propane nitrile will exhibit optical isomerism. Now the compounds that form in this reaction exist as racemic mixtures or racemates. Now a racemic mixture has an equal number of moles of each optical isomer or enantiomer, and therefore the ability to rotate plane polarized light is cancelled out because 50% of it will rotate the plane polarized light to the left and the other 50% rotates it to the right, and therefore you observe no optical activity. So now let's look at the mechanism for this reaction. So I'm going to draw ethanal, and ethanal has a CH3 attached to a C double bond O H. And ethanal contains a dipole. The carbon is delta plus, the oxygen is delta minus. This is because oxygen is more electronegative than carbon. And I'm going to put in a lone pair of electrons on my nucleophile, which is Cn minus, and this lone pair attacks the delta plus carbon. Now this causes one of the bonds in the double bond to break, the pi bond, and the result is the following intermediate. We get a CH3 attached to a carbon which now has a bond to the cyanide, and the double bond has been broken and we now have O minus. Now I'm going to put in the lone pairs of electrons around the oxygen, and I'm putting 3 pairs of electrons around the oxygen because there was 2 lone pairs around the oxygen in the C double bond O, and I've added another pair of electrons when the double bond broke. And this pair of electrons attacks a hydrogen in hydrogen cyanide. The hydrogen cyanide bond breaks, and therefore when the hydrogen cyanide bond breaks, there's a H plus which can add to the oxygen in the intermediate to form an OH group, and I've got my final product. Now, instead of drawing the arrow from the oxygen pair of electrons to the HCN, I could have drawn it to a H plus. That would be perfectly fine. Now, the way I've drawn it, I've shown that the hydrogen cyanide bond breaks for you to generate the Cn minus and for you to generate the H plus that adds to this O minus intermediate. Now, there's 2 steps in this mechanism. The first step is the attack of the nucleophile on the delta plus carbon. So a lone pair of electrons attacks the delta plus carbon and the double bond breaks. That is a slow step. And the fast step is a lone pair of electrons on the O minus intermediate attacking the hydrogen cyanide molecule and effectively attacking a H plus that's formed from the hydrogen cyanide molecule breaking. That's a much faster step. Now, there's also 2 coordinate bonds forming here. There's a coordinate bond forming between the cyanide and the carbon because a lone pair of electrons have moved towards this delta plus carbon. And there's also a coordinate bond forming between the O on the O minus and the hydrogen to form OH. Now, the compounds that form in this reaction are hydroxynitriles, and they're also sometimes called cyanohydrins. Now, the reaction is useful as the nitrile group can undergo hydrolysis in acid conditions to form a carboxylic acid group. So when you add a CN into a carbon chain, you have to be aware that you can hydrolyze it in acid conditions, so you reflux it with a dilute acid such as sulfuric acid, and this CN can change to a COOH. So if you ever see a cyanide group in a molecule, be prepared to be asked how you change it to a COOH, and you do this by refluxing it with dilute acid such as sulfuric acid. Now, you can also see from the equation at the bottom that you could use dilute hydrochloric acid to hydrolyze this. Either's fine. Any dilute acid would cause the cyanide group to be converted to a COOH. So now let's test your understanding of nucleophilic addition with some practice questions. So here's our first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So in question 1, you're asked to complete the equation below, which shows the reaction of benzaldehyde with hydrogen cyanide. Now, benzaldehyde is an aldehyde because it contains a benzene ring, an alkyl group attached to a C double bond O and a H. And when you add hydrogen cyanide, the hydrogen cyanide adds across the double bond that breaks. So all you have to do is break the double bond. You put the hydrogen next to the oxygen to make an OH, and the cyanide adds on, so you're left with a benzene ring attached to a carbon which is bonded to an OH, a hydrogen and a cyanide group. And then for part B, you're asked to give the formula of the nucleophile that takes part in the reaction Well, the nucleophile is Cn minus, and you really should put the minus on the carbon, but they did accept it if you wrote Cn minus. So now have a go at part C. So once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. So for our first question, we have a 5-carbon ketone. Now this ketone is called pentan 2-one. So we have a CH3 attached to a CH2, attached to a CH2, attached to a C double bond O, bonded to a CH3. So this is pentan 2-one, and I'm going to draw it out in full so you can see what happens when we add hydrogen cyanide to it. So pentan 2-one reacts with hydrogen cyanide, and my product will have a CH3 group attached to a CH2, attached to another CH2, attached to a C, and this time the double bond is broken and becomes OH. The cyanide adds on to this same carbon as well, and then this is bonded to a CH3. So I formed my hydroxynitrile, and the name of this hydroxynitrile would be as follows. What I have to do is I have to find the longest chain that contains the CN group. So I'm going to circle this now. Now this is 5 carbons long, so this is going to be pentane nitrile, and I'm going to number the carbons. So the CN group is carbon 1. Now if I look what's attached to this chain, I can see that I have an OH group on carbon 2 and I have a methyl group on carbon 2, a CH3 group. So this compound is called 2-hydroxy 2-methyl pentane nitrile, and the hydroxy is written before the methyl because it's alphabetical order. Now when writing chemical equations in organic chemistry, it's perfectly fine to draw out the full structural formula of compounds. In this case, it makes it easier to see that the hydrogen has joined the oxygen to make an OH, and the cyanide is joined onto the same carbon. You could, however, use shorthand, and you could just write down the product is CH3, CH2, CH2, COH, CN, CH3. That would be fine as well, but I've chosen to draw out the full structural formula to make it easier to understand what's happened. So now let's have a go at question C part 2. So the compound that's being reacted with HCN here is an aldehyde, and it's got 1, 2, 3, 4, 5 carbons in. So the aldehyde is going to be pentanal. So pentanal has a CH3 attached to a CH2, attached to a CH2, attached to another CH2, which is attached to a C double bond O and a H. So pentanal is a 5-carbon aldehyde. Now, when pentanal reacts with hydrogen cyanide, the double bond of the C double bond O is going to break, and the hydrogen cyanide is going to add across this double bond. So my product is going to be CH3, CH2, CH2, bonded to another CH2, and then I'm going to break the carbon oxygen bond, the double bond, and I'm going to have a COH. The cyanide is going to join to the same carbon, and a H. Now that is a hydroxynitrile, and to name this hydroxynitrile I need the longest chain that contains the CN group. So this is now 6 carbons long. So I'm going to number these carbons: 1, 2, 3, 4, 5, 6. So this compound is going to be called hexane nitrile. It's going to end in hexane nitrile. And the OH group is on carbon 2. So this is going to be called 2-hydroxy hexane nitrile. And once again, I've decided to draw out the full structural formula to represent the equation because it's easier to understand what's happening that way. So now have a go at question 2. Question 2 is asking you to classify the type of reaction taking place when propanone reacts with hydrogen cyanide, and then it's asking you to draw the mechanism for this reaction. Pause the video, have a go at the question, and then we'll go for the answers. So now let's go for the answers to question 2. So the type of reaction taking place is nucleophilic addition, and you get 1 mark for that. And then you have to draw the mechanism. So I draw propanone out, CH3 bonded to a C double bond O next to a CH3. I'm going to put the delta plus on the carbon and the delta minus on the oxygen. Then I draw my nucleophile, Cn minus. A lone pair of electrons from the nucleophile attacks the delta plus carbon. This causes the double bond to break. So I draw an arrow from the double bond to the oxygen. Now this leads to an intermediate being formed that consists of a CH3 bonded to a carbon, which has a Cn, an O minus attached and a CH3, and a pair of electrons from this intermediate, a pair of electrons on the oxygen, move towards a HCN, and the HCN bond breaks, and this generates a H+, which attaches to the O- to form our final product, which is 2-hydroxy 2-methyl propane nitrile. There's 3 marks available for this mechanism. So 1 mark is given if you drew Cn minus with a pair of electrons attacking the delta plus carbon. So if you drew in the nucleophile and a double-headed arrow moving from the pair of electrons to the delta plus carbon, that gets you 1 mark. If you had the correct dipole, delta plus carbon, delta minus oxygen, and then that double bond break in, and you drew a double-headed arrow moving from the bond onto the oxygen, there's a mark for that. And the final mark is given if you drew an arrow, a double-headed arrow, from the pair of electrons on the oxygen, from the O-, attacking either a H+, or you could do like I've done, attack a HCN molecule, and that causes the bond to break. So here's our last practice question for you to have a go at. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 3a is asking me to draw the mechanism of the reaction of hydrogen cyanide with pentan-3-one. And it's asking me to show appropriate charges and curly arrows to represent electron pair movement. So I'm going to draw the structure of pentan-3-one, and pentan-3-one is a 5-carbon ketone that has a C double bond O group on carbon 3. So I've drawn a CH3 attached to a CH2 attached to a C double bond O attached to a CH2 and a CH3. Now I'm going to put in the dipole on the CO, the delta plus carbon, delta minus oxygen, and then I'm going to draw in my nucleophile, which is Cn minus, and I'm going to put a pair of electrons on the carbon and a minus charge on this carbon, and the pair of electrons attack the delta plus carbon, so I've indicated that with a double-headed arrow, and then the double bond breaks and a pair of electrons go onto the oxygen, and then I draw my intermediate, and my intermediate is going to be CH3 attached to a CH2 group, and then this CH2 group is going to be attached to a carbon which has a cyanide joined to it via a coordinate bond and an O minus. And then this has a CH2 and a CH3. So there's my intermediate. Now the first step is quite slow, and this last step involves a pair of electrons on the oxygen attacking a hydrogen cyanide molecule. And I'm going to put in the pairs of electrons, and this now attacks a HCN. Now I could just draw H plus here and it attacking a H plus, but I've chosen to draw HCN. So the pair of electrons attacks the HCN. This causes the HCN bond to break, and that's how you have a H plus for it to attack. And therefore I'm left with CH3 bonded to a CH2, and this CH2 here is bonded to a carbon that now has a cyanide on it. It has a OH on it, and it has a CH2 CH3. Now notice that this actually doesn't form a chiral center here because there's two ethyl groups attached to this carbon next to the OH and the CN. So to name it, I'm going to find the longest chain that contains the CN, and this is 4 carbons long. So this is butane nitrile. I'm going to number the carbons, and if I number them, I have an OH group on carbon 2, and I have an ethyl group on carbon 2. So this is going to be called 2-ethyl 2-hydroxy butane nitrile, and that is my hydroxynitrile that's formed. So 2 marks was awarded for this mechanism. 1 mark is given if you got the nucleophile correct, attacking the delta plus carbon, and then that bond breaking, the double bond breaking, so a double-headed arrow moving from the double bond to the oxygen. So if you've got that, there's 1 mark. And the second mark is awarded if you had a lone pair of electrons on the O minus attacking either a H plus or a HCN. There's 1 mark for that. Now 3A part 2 is asking you to explain whether the reaction is classed as nucleophilic addition, and this is because it involves attack by an electron pair donator, the CN minus, and overall addition of hydrogen cyanide across the C double bond O double bond to form a single product. So the idea of the reaction involving attack by an electron pair donator gets you a mark, and if you said that the hydrogen and the cyanide add across the double bond to form a single product, that gets you the 2nd mark. Now for question B, you're asked to draw the displayed formula of the product you get if you hydrolyze the product formed in part A with dilute acid. Now you have to remember that cyanide groups can change to COOH groups if you hydrolyze them with dilute acid, and this is carried out by refluxing the compound with dilute acids such as dilute sulfuric acid. Now all that I've done here is just get rid of the CN and draw a COOH group. So you're asked to draw the displayed formula, 1 mark for that, and then you're asked to name it. And to name it, all I do is I find the longest chain containing the COOH group. So the longest chain is 4 carbons here. So the carboxylic acid that's formed is going to end in butanoic acid. There's an ethyl group attached to carbon 2, and there's a hydroxy group attached to carbon 2. So the name of the compound is 2-ethyl 2-hydroxy butanoic acid. So 1 mark for drawing the structure and 1 mark for naming. So that concludes this video lesson. So after watching this video, you should now understand that aldehydes and ketones react with hydrogen cyanide to form hydroxynitriles, and that these reactions are examples of nucleophilic addition. You should also be able to write chemical equations and reaction mechanisms to describe these reactions, and be aware that hydroxynitriles undergo hydrolysis reactions to form important hydroxyacids. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.